So in today's tutorial class, we'll be covering Australian rainfall and runoff. So at the beginning, I'll show you the rainfall data hub or the Australian rainfall runoff data hub that gives a lot of information to us. So let me share your screen. So can you see my screen?
Yes,
so you can see my screen, is that right?
Yes.
Okay, so in this ARR, if you come to the data, then you will see that it has a data hub, ARR data hub. So if you click it there, then it will give you a window-based map. And then we have to put the latitude and longitude of the your catchment location. So catchment means that we can draw the catchment boundary, and there is a outlet of the catchment where the runoff is being accumulated. So that is at that point we have to give the longitude and latitude. So so really then we can obtain a lot of information. The river region, area reduction factor parameters, storm losses, temporal patterns, area temporal patterns, BOM IFD depths, median pre-burst depths and ratios, other pre-burst depths and ratios, then interim climate change factors, and we can select all of them, and also the base flow factors. And then if we submit it there, then really it will show you a lot of information. So it will give you the division, Southeast Coast Division, basin number, river number is 13. River name is Sydney Coast Georges River, for example, this one. And we can see the catchment, the Georges River catchment. So that is our river region. And then we can look at the ARF, aerial reduction factor parameters. So for this location, the generalized equation of ARF is written in this way. And then can you mute yourself? If somebody is talking, please mute yourself. So this is for Southeast Coast zone. The coefficients here, A, B, C, D, all these coefficients here, they are given here for your this particular location. So for short duration ARF, we can use this equation here. So at this location, what are the loss values? Storm initial loss is 28 millimeter, and continuing loss is 1.6 millimeter per hour during the rainfall events after the start of the runoff. So then we have the temporal patterns here, and we can download the temporal patterns from here as zip file, and then we can unzip it, and then we can use it. So if we download this file, for example, temporal pattern file, and then let us look at it in folder. So you can see here that this is the burst duration. So, and then really you have to, this is the burst duration here. So, and this is for a particular return period they are given. So this is a temporal pattern data.
So you're not sharing that screen.
Oh, this, we cannot see this, okay. Sharing the previous screen. So if I say screen share, then it should really go sense it. So can you see it now?
Yeah, that's fine.
So it's really giving the different event ID, and it's giving the location. Original burst depth is 15.5 millimeter. It's within the frequent event. AIP is in percent. AIP is this. This is the burst start. So it's a historical event basically. And then this is the burst end time. So basically it is giving the each of the events that have been used in the derivation of the temporal pattern. So we have another file, which is so can you see another screen here?
Yep.
Yes, sir.
So another screen here, and we can see here that these are the temporal patterns. So you see 10 minutes duration and 5 minutes is time steps. So for the first 5 minutes, the rainfall is 58.06%. And for the second 5 minutes, it is 41.94% of the rainfall happened for that event ID. If you take another event which has 10-minute duration, it is first 5 minutes is this percentage, second 5 minutes this percent. So you can see that there are a lot of variation is there when you are taking about 15-minute burst. So this is 15 minutes here. You will see that each event is 5 minutes, each increment is 5 minutes. So 3 times 5, 15 minutes. And then you have the temporal pattern. If you add this up, 47, 28, and 24, it's 100%. So it means that in the first 5 minutes, rainfall has happened 47.11% rainfall, and then 28.1% of the total rainfall, and 24.79% of the total rainfall that has happened in the last 5 minutes. So these are all the 15 minutes events, similar 20-minute events. So really, if you go more than 360 minutes, and if you go so you see it has gone up to 10,080 minute. And in that case, you will see that it has a lot of increment, 180 increments. So really this data will be quite long. So these are all the temporal patterns in that division. So you have to select the appropriate temporal pattern that you want to use for your design. Okay, so I have to stop share again and share screen again, this one here. So this is the temporal pattern. Then you have aerial temporal pattern as well. Then IFD here. IFD means that I think we already showed you how to do the IFD. So IFD is really the Bureau of Meteorology, that the IFD calculator. So at that particular location, we can ask for any duration, or we can ask for the standard duration here, and we can ask the rainfall is better millimeter per hour in unit, and then you have the different rainfall, which is the very frequent. If you go for very frequent, and if you say very frequent, then what you will get? You will get it like you see 12 event per year, 6 event per year, and for different duration, you go to your rainfall intensity in millimeter per hour. If we go for frequent and infrequent, which is the most widely used, the middle one, and then if we go to rare, then let us see in rare what we get. So let us go for rare. So we see for rare, for 1 minute duration, for 100-year return period, the intensity is 386 millimeter per hour rainfall. And for 2000 return period is 557 millimeter for different duration. So that is basically our IFD. I think we discussed IFD before. You can get the graph of this as well. You can, if you ask for chart, then you'll get it the chart of the IFD as well. So this is the rainfall things from the IFD. So I go to your screen sharing. Okay, so now so when you say biome IFD, then it will give you some standard data, but you can get it from there directly there. So these are the pre-burst rainfall depth. So there are different, like all different types of rainfall burst there. And then we can get the information like the area of the catchment is 771 kilometer square, catchment number, and also you can get the base flow factor. Base flow factor means that the fraction of the like the runoff coming from the rainfall divided by the total stream flow. So that is the base flow factor. Sometimes base flow is important when you want to use the rainfall and runoff. So do you have any question on this? Any questions on rainfall runoff data hub? Now, if you don't have questions, then let us solve the problem in our tutorial question. So Okay, so let us look at the tutorial question today. So can you see the tutorial course, tutorial 10?
Yes, sir.
So if you can do this question by yourself, I think today you should be able to do it yourself. So question 1, what is Australian rainfall runoff? So can you tell me about what is Australian rainfall runoff?
There's like a guidebook for flood estimation in Australia.
That's right. Yes, it's a guidebook for rainfall runoff modeling, flood estimation, urban hydrology, this kind of thing. How many editions ARR has?
I think that this is the fourth one, AIR 2019.
Yeah, there are 4 editions. So 58 are the first edition, and then the latest edition is 2019 edition, we are calling it. Although it started operation from 2016, that's why you'll see some of the things within the ARR 2019 is still in 2016. So 2016 is the interim version, and 2019 is the final version of that 4th edition of the ARR. So now, can you find out the design rainfall for this catchment by yourself, everybody? So latitude is there, longitude is there. Find the design rainfall intensities for 10% and 1% AEP for 6-hour duration from Australian Bureau of Meteorology website. Okay, can you do, everybody? Can you do it, and then I'll see the answer. Anybody has any difficulty in finding the IFD calculator? If you have no difficulty, then please do it. And if you need my help, please let me know. Ali Ahmad, can you find it? Ali Ahmad?
Yes, sir. I am trying, sir.
Okay.
I got 158 for 10% and 276 for 1%.
What's the unit? Is it millimeter? Millimeter per
Yep,
hour?
yep. Millimeter, yep.
Millimeter. Okay. So we have to be careful about the unit.
Yeah, so I got Got a 13.4 and 20.7
What's your unit?
millimeters per hour.
That's right. Millimeter per hour is the better unit in my opinion, because then you can understand the differences better.
Yeah, the question asks for rainfall intensity. Yeah.
That's right. So millimeter per hour is a better way of doing it. Otherwise, it creates confusion because for a big duration, then your I think standardized unit is better millimeter per hour.
Sir, is a GEV distribution used to estimate?
What is the probability distribution that is used to derive this IFD data? It's GEV distribution.
Yeah, that was my question.
Yeah, that's right. It's a GEV distribution for the range of up to 100 year return period. But for frequent rainfall estimation, it was not GEV. It was generalized Pareto distribution
Okay, thank you.
with POT, partial peaks over threshold series. So it is a partial, they use partial duration series that we discussed in one of the lectures, that they use the all the values over a threshold, all the independent values over the threshold, and they use the generalized Pareto distribution for estimating frequent rainfall, and for the within our normal range, which is basically 1 year to 100 year, the GV distribution, and also for from 100 year to 2000 year, that is also GV distribution.
I'm sorry. You know how we convert the AEP to ARI by doing the reciprocal? For example, AEP of 50 will be 1 over. Sorry, an ARI of 50 will give you corresponding AEP of 1 over 50. But in the ARR and also on the IFT website, it says that it doesn't always correspond like that, because
You're right. I think you have asked a very important question. The guideline that is given in ARR, which is more accurate. So to be precise, we should use that conversion. But for general purpose, we can use that AEP equals 1 over T for general purpose, but it is not very accurate.
I'm so just asking because for my thesis, I've done the general conversion, of course. I haven't taken the conversion that they do here. So will that be a problem?
No. In your thesis, you have used we have given it the flat contrast estimated. So that has been estimated by considering all the factors. So you don't worry with that. And then you are using the rainfall intensity there. So in your case, there is no issue.
So like I'm asking this because some of the data were used derived from the flag software, which was as ARI, but I have taken used the data from my thesis, but I have converted that to, of course, AEP percentage by using.
That's all right, because the flag software, they have used the conversion that I am AEP equals 1 over return period.
So like, is there an explanation as to why it doesn't like convert?
Because there's an equation, there's a precise equation how the AEP and return period is related. And that equation is not that simple. It is a little bit complex equation. But most of the people, they don't bother with that conversion. But since it is national standard guidelines, so they have to give the more accurate version. But most of the people use that AEP equals 1 over return period, 1 over ARI.
Thank you, sir.
But it's good to know it. Okay, so everybody got the rainfall intensity value? Ali Ahmad?
Yes, sir. I would like to check with you, sir, whether what is I found.
How you found?
Yeah, for 1% AP, it is 276.
Yes.
Am I right, sir?
And 10% it is millimeter.
Yeah, it's millimeter. And for 10%,
can you click on the top button? There is a millimeter per hour. So tell me the in millimeter per hour.
yeah, millimeter per hour. Yes.
So how much is that?
Yeah. So now it is 46 for 1% AP and 26.3. It is for 10% AP.
That tends to be too much. Sanjeev, how much you got?
Yes, I got that. For 10%, 26.3 millimeters per hour, and 1% is 46 millimeters per hour.
Yeah, it's the same for me, sir.
Okay. So everybody got the same answer, similar answer?
Yes, sir.
Yes.
Okay. So if anybody has got any problem or any issue, please let me know that I can help you. So now for any location that you should be able to find out the IFD, this is very, very useful information for all the stormwater design, all this kind of problem. You need the IFD, and it is so easy to use now. In the 1987 version, it was quite complex. You have to use the hard copy map, and then you have to interpolate it, and then you have to put that in a program, and all complex. But in ARR, this ARR, everything is computerized. So life is very easy. You put your latitude, longitude, and then you get your data. But thousands of computations is being done to come up with this answer. Do you know what is the degree of accuracy of this IFD estimation? How accurate they are? Say for 1% AEP rainfall estimation that you got it here for 6-hour duration, what kind of accuracy is there?
1 decimal place.
How much?
I think it's 1 decimal place, or 3 significant figures.
It is significant figure. That's one thing, but I am after in terms of percentage. Is it 5% error, relative error, or 10%, 20%, 30%, 50%? What could be the error? It is not 100% accurate. It has a confidence limit. So in terms of accuracy level, generally if the catchment in the mountainous area, slope is very high, steep mountain area, your error level is generally higher. And sometimes error level can go 30% to 50% error is there. So the error in rainfall estimation is smaller than the error in flood estimation, because the flood estimation error includes the rainfall estimation error as well, plus other error as well. So that's why flood estimation has higher error than the rainfall error. Okay. Okay, so
Sorry, I had a question. Yeah,
please.
regarding the ARR, the RFFE model in the ARR, I've seen that the error level is around 50% for that. So let's say if someone uses that model to construct a dam or something, for example, if using that model, you get a 100-year flood of 1,000 cubic meters per second. So because the area is so high, 50%, so do they consider, like, do they increase the value by 50% to make sure that it's safer?
It's safer, that's right. Yeah, it depends on the consideration of the design team and the department they are using it. So ARR does not give any guideline. So it's up to the department or the owner who are doing it. So Australian Rainfall does not want to take the responsibility. So you have to make a decision. Like most of the time, depending on the importance of the structure, you consider this kind of things. Like for structural design, we use the factor of safety in the design. Is that right?
Yeah.
What is the factor of safety we generally use in concrete reinforcement? If you are designing a concrete slab or beam or column, what is the factor of safety we consider? Any structural engineer here? You're all civil engineering, most of them, so you should know factor of safety, how much factor of safety you use.
So I think it's like 2 or like 1.5 to 2.
Something like that, that's right. So it means that 1.5 means that you are 50% increasing, is that right?
Yeah.
And 2% means that you are increasing your value by 200%.
Yeah.
So for compressive strength of concrete is say something, and then you are really multiplying that by dividing that by 2 in your design basically. So that means that you are considering a smaller compressive strength so that your structure does not fail because you will design it heavily, more heavy. Still then your structure fails. Because engineering is not a precise science. Engineering is a approximate science. So we are trying to use the best available knowledge and information And in many cases, our estimation is not 100% right, but we try to give the best possible thing. It's like a medical science. Like if you have a disease, you go to doctor, different doctor will diagnose in a different way. They'll give you in a different types of medicine, and all different sorts of things will happen with you. But still, you cannot say really, I want a precise medicine which will really cure me. It's very hard to tell most of the time. Okay, so then slot frequency chapter, we asked you to read it before, and I said that I will ask you some questions. So did you read it? Anybody read the book 3, chapter 2? Is there any student who tried to read it?
I read it before, like not today.
Okay, so before that's fine. Did you have any question for me?
No, sir, not now.
No. If you don't have any question, then I'll ask you some questions about this chapter. So can you tell me that what are the probability distributions they have included in ARR, that chapter, for flat frequency analysis?
So the log Pearson type 3, then GEV, then EV1, the Gumbel distribution, I think that's 4. Maybe there's one more.
Now EV1 is really Gumbel. Gumbel and EV1 same.
Okay.
Any other distribution you missed? Anybody else? Generalist Pareto is another one. So log normal, EV on, log normal, Gumbel, LP3,
And GEV.
GV, GPA. So they have given distribution of 5 examples. So it is expected that your data, your site should fit one of these distributions. Generally, we can assume that. So in Aston Rainfall around 1987, they recommended you to use LP3 distribution. But here they have not recommended any distribution. They have not even talked that you can use any 5 of this, because they don't want to take the responsibility, because if something happens, then everybody will blame the ARR. And then if some structure fails, and if somebody dies or some property damages, then they may file a case in the court. And then they will say that Australian Rainfall recommended this, so I have used it. So that's why ARR doesn't want to take the responsibility. They say this is a guideline, but if you can use it, use it. But if you don't want to use it, use something else, but you have to defend yourself. So really, you have to be really judgment, like you have to use a lot of judgment and that's like your knowledge to select the right distribution when you are doing flat frequency analysis. But this is widely used, like designing a wall, bridge, culverts, all this kind of infrastructure. You need to do flat frequency analysis, either at site or regional. Then in question 4, can you estimate your 1% and 10% AEP design floods at location in New South Wales for these 2 locations? So these are the data given in this table. So can you go to the ARR RFEP model and use the regional flood estimation model to obtain these design floods? If you have any difficulty, let me know. Is Saika here today, Saika?
Assalamualaikum, Prof. I'm here.
So after this problem, if you can release the result to the student, discuss the result.
I can.
So if you want to show the probably we cannot show the results to everyone.
Yep.
Because they can get it from the views, but what you can give the general information about the result, like highest, lowest, this kind of thing.
Yep.
Mean, median, who got, how many students got pass, distinction, high distinction, and who got the highest, you can tell that. Who got the highest, second highest, you can tell that, that's fine, but we cannot disclose the results in front of everybody for every student.
Okay, Prof.
So Gokan, are you taking the attendance?
Yes, sir. Yeah, I did.
Okay, that's good. Have you seen your paper published?
Yeah, I checked it. Thank you very much for the good news. Yeah, I'm very happy.
They have published it very quickly.
Yeah, that's really good.
Because I sent the proof last night, basically.
Yeah, within a week. I wasn't expecting that quick, to be honest.
They're very quick. Yeah.
But yeah.
It's like really high discharges for these two stations from the RFP model.
Okay, so what is the discharge for your Unjela at Oxley Creek?
So for 10%, it's 10% AP, it's 2,420 cubic meters per second. And for 1% AP, it's 6,980 cubic meters per second.
Okay. Because this catchment area is quite big, 213 per kilometer. It's not a very small catchment. So and then have you done the next one?
Yes.
So what are the estimation there?
So for 10% AP, it's 2,040 cubic meters per second. And for 1% AP, it's 5,900 cubic meters per second.
Yeah. So yeah, our RFP model is basically it's doing a lot of it's regionalization approach. Similarly, IFD is also regionalization. So IFD estimation is trying to use the data from nearby stations using ROI approach. Similarly, the RFP model is doing the same thing. Basically, the same approach. In fact, certain Bureau of Meteorology, they borrowed our approach because we developed our approach first, and then we then upgraded our approach for them. Other than we did that. So it's very similar approach, but different distribution. Here we have used LP3, they have used GEV, but the approach is very similar. Any other student you have done it? Ayman, have you done it, Ayman?
No, sir, I'm just reading the file.
Okay. So Ivan, you got it?
Not yet, sir. I'm just not yet. I'm just working on the Excel
For me,
file.
Ali Ahmed, can I share my findings?
You got it? Okay, tell me.
Yeah, for 10% AEP, it is 2,420 meter cube per second. This is the discharge, and for 1% AEP, it is 6,980 meter cube per second.
So that is for your second catchment, is that right?
Yeah, the first customer, sir.
First catchment,
Anglia.
okay. So is it different than Tanzim? What you got Tanzim is the same?
No, it's the same.
Because it's coming from the same software, so it should be same.
Yeah. Okay, so now I can try for the second one.
Yeah. It's so easy to use. Life is so easy. Just you put your 4 latitude, longitudes and catchment areas, then done. But it has calculated, done thousands of calculation behind it. I hope all of you have done it, is right? I have
yes.
not done it yet.
Yes, sir. I'm just on the website now. Just plug in the values so I can get the values.
Any of the students having difficulty? At least if you can find the software from the website, then you're done. Then you just plug in the values. Can you download the data, like the output? There are some text file generation there in the program. You can see there are some text files that you can generate. Can you generate those text files and see what are the results inside?
So it's just giving the discharge for the APs and also the percentages and the mean, standard deviation, and skewness.
So what are these mean, standard deviation, skew?
The ordinary moments. Oh, the
So-
actual values.
So these are basically the when you convert the data into log, annual maximum series at a particular location, and then you have the mean, standard deviation, skew, which is basically the parameters of the LP3 distribution, and that is coming from there. And also there is a correlation matrix. Can you see the correlation matrix there?
Yes, sir. Yes.
So this correlation matrix and these values are used in using a multivariate normal distribution to develop the confidence limit by Monte Carlo simulation. So you generate 10,000 values of the flat quantile by assuming that your parameter estimation is not fixed, rather it has a probability distribution. And then you generate 10,000 sets of parameters of the LP3 distribution, and you estimate 10,000 different values of your, say, 1% AAP flood. And then you rank them and you obtain the 5%, 95% limit of those vector, and that gives you the confidence limit of that you see in the ARR output.
Sir, if you don't mind, I just have one question.
Sure.
So for the catchment
Yes.
outlet,
Yeah.
do we put the gauge let and for the catchment?
Yeah, I think you're right.
Outlet.
Outlet is the gauge lat and gauge long.
Okay, and
First
then
one,
yes,
and the centroid is there. Centroid is the other one.
yes, sir. Thanks. Yeah, should be in the right direction.
Outlet means that where we have the gauging instrument, that is, we call it outlet in this kind of subject.
So have you marked the roll?
I think Gokhan is doing it. I think Gokhan is taking the attendance.
Yes.
Okay. Can I get my name marked off because I've got to go to a meeting with my supervisor at 4.
That's fine. That's fine. You can go.
Thank you.
No worries.
Do you want me to just put it in the chat? Put my name in the chat with the student number?
No, all good. I did it. All done.
Okay, perfect. Thank you.
No worries.
Okay, so I think we can probably go to the mark release now. Maybe I think sure he will be able to do it. If
Yes,
you have
yes,
any
I'm done.
difficulty.
Yes,
Done?
I'm done. Yeah, I found it. I found the tables. Like I found everything.
So during exam time, you may expect a question from these kind of things, IFD and RFFP, because it's an open book exam, so you can use your computer and your website, and you can get some values. We'll give you some location like this, and then you have to obtain different things. We'll ask from ARR website, basically, RFFP
Yes,
software
sir.
and also the IFD estimation.
Yes, sir. Should be fine. Thank you.
It will be very easy for you if you know it, and it's very,
Yes.
very useful in your career, in your like every design, every like you need to use this kind of software. Specifically. Okay, so now Saika, can you? I will stop share so you can take over and you can give us the result.
All right, Prof. Thank you, Prof. Can you see it, Prof?
Yes, I can see. Yes, we can see. All the students should be able to see it, I think.
Can
Yes.
all of you see it?
I can see.
Ali Ahmed, your result is not here. Sorry. I will just give you later.
Okay.
Yeah, like the postgraduate student will be given later. This is the undergraduate students.
Okay, we just wait for the result. And see
Yeah.
So
how
it's really a lot of students fail, is that right?
Yep, lots of students fail because in the regression analysis, most of the students did the wrong thing. They just didn't read the question carefully. That's why they didn't decide what to do.
So it's really 26% students failed.
Out of 50, 26 students failed, more than half.
More than half, 50% students failed.
Yep,
And then 2 students got, 3 students got high distinction.
yep.
Who are these students got high distinction?
Mac Alistair Aaron,
Okay.
and he got the highest, 55.5. And then Tanjim, he got 55. And then Brooke Alex, she got 51.5, I think. These 3 students just got distinction.
So congratulations, these students who got high distinction and who got past everybody. So yeah, I'm a bit surprised by seeing that so many students failed. Can you explain the solution maybe to a
Yeah,
student?
Prof. I can explain. Most of the students, many students did the wrong regression analysis because they did separately. They did the regression analysis separately for each flow, but you asked them to do it by a single regression analysis by using the 2 flow.
That's right. That's right. Yeah.
But they didn't read the question carefully, I think. And some students use the T distribution, Z distribution value instead of T distribution value. So
They use the standardized normal distribution, but they forgot that this is a sample.
Yeah.
They have to use T distribution. So they have used the standard normal distribution, which is not right.
Yeah.
But for that, you have given some mark, I guess.
Yep, I have given them half marks,
Okay.
50% marks.
Miss,
Yep.
I haven't got my results back.
Can you please say your name? I can't see
Uh,
your.
Ayush, AYUSH.
Oh, you want to see the marks?
I will release the mark for every student right now in the views.
Okay, thank you.
So I'll release the mark in the views very short, like in after the class basically, so you'll be able to see it, or maybe I can do it at the same time when Saika is doing it.
Yep, Prof, that would be great.
Saika, you can just explain the answer, then I'll release the mark.
Okay, Prof, thank you. Here, for the GV distribution, the results are like 1000 to 1150 in between this range. And some students, you put the wrong scale. You put the standard error scale instead of the estimates. So I deducted some marks there. And for number B, Prof, can you please explain the number B?
Okay, so if you go up, that your distribution and the standard error, I'll explain a little bit. Go up.
Yep.
So here you can see that the estimate of the location, scale, and shape parameters. So these are 240 location parameter and scale parameter and shape parameter, and the standard error of those values. So standard error higher means that it's more error in the estimation of the parameter. So you can see that standard error of the shape parameter is very high because 0.18 and the error is 0.12. Standard error, so it's very high. So that always happens with the shape parameter. It's not easy to estimate it. And then of course you have to use the estimates of the location, scale, and shape parameter, not the standard error when you will be estimating the quantiles. So okay, come down further.
Yep, Prof.
So what are the question? Sources of uncertainty, is that right?
Yep,
Something?
Prof. Sources of uncertainty. Yep.
So the sources of uncertainty, we are, how many uncertainty? We asked 5, is that right?
5, yep, Prof. 5.
5 uncertainty we asked. So the students who got the highest mark,
Yep.
I think it will be difficult to share at this moment. But really, we gave, I think, 2 marks for each uncertainty that
Yep.
we mentioned.
And some
One,
people
of
just-
course, should be on the record length, that the limited record length we have here.
Yep.
We are estimating, say, 100-year flood, but our data length is not that much.
Yep.
So there will be uncertainty from their sampling uncertainty. Then there will be uncertainty in terms of parameter estimation, particularly in the estimation of the shape parameter, because shape parameter has a lot of uncertainty in it. So that will affect your estimation as well. That is number 2. Number 3, you can mention about the, we are assuming that the data is stationary. It means that there is no trend in the data, so that our parameters, they are fixed or not changing with time. So that is that is not the case nowadays. So basically, we have to do non-stationary flood frequency analysis, or we have to consider the trend in the data or the impact of climate change. So that is another estimation error there. And then another type of thing that we are using here for estimation of the parameters of the distribution, we are using method of maximum likelihood. So method of maximum likelihood is very good if we know the population. But in this case, we have only the sample, which is not the population. So it can give quite a lot of error. So alternative method could be the L moments method and so on. So these are the different sorts of uncertainty and things. And I know it's hard, but some students, they have done well.
Prof, can
but
I say here something?
Yeah.
For each point, we have 2 marks, but
Yeah.
most of the students just said that it's the climate change effect. They didn't explain, so I deducted mark for that.
Okay, so you can get some marks for that, yes.
Yeah. And it is number C, the 1% AP.
This is the confidence limit, is that right?
Yeah, confidence limit, yeah, Prof.
Okay, so for the confidence limit, student, you have to use your T distribution.
Yep, this is the
Some of the
table.
students you have used normal distribution, because normal distribution can be used if
This
you
is-
know the full population. But in our flat frequency analysis, we never know the population, it's a sample. We have to
Sample.
use the T distribution, and the T distribution is depends on your significance level and the degree of
Degrees
freedom.
Yeah.
So your degree of freedom, and then
48.
your 50 is the degree of freedom, which is the n, and
No,
then n minus 1,
N minus 1, 48.
48.
Yep.
Okay, so that is your degree of freedom, and then you have to see, we have asked 90% confidence limit, is that right?
Yep, Prof.
So on each side is 5%, so you have to take 1.676, is that right?
Yep.
Okay, and then really,
1.677. 1.677.
that's right. So mean plus minus 1.677.
Yep. Then it is.
So this is the confidence limit that you have to do. So
Yeah.
the lower limit is this, upper limit is this, 221 to 320. So the
It will
students who
vary.
got very high marks, they have used T distribution, is that right?
Most of the students did it correctly.
They have used T distribution, is that right?
Yep. Most
Oh, that's
many
very good.
students did it correctly.
Very good.
They got less marks in the uncertainty and accuracy in the next question. The
Okay, so,
descriptive two question.
okay, yeah.
And now it's number 2 question. Here
Yeah.
I did regression analysis for you.
Yeah.
Please see it carefully, everybody. Most of you just did it wrong.
Miss, excuse me, how do you get all the points in like the same graph? Because like we tried and like it showed two different trend lines. We can't get one trend line when copy pasting the information in the same chart.
Is it?
Because you have to use only the flow data when you are doing the plot. You want
Yeah.
to regress the flow data, not the time. So basically, where you have gaps, that should be your Y values. And while you don't have any gaps in the data, that should be your X values. And then you use the flow data and then plot it, flow 1 against flow 2. Is it clear to you now?
Yes, sir.
not clear.
We did that. I showed that in the example in the class.
Prof, many students just tried to did it manually by calculating X, Y. It's very hard. They just didn't do the simple version.
Because I did that in a tutorial class, and really students sometimes they don't listen, they don't ask question. So I assume that everybody have understood it. So I explained it very well in a class. I showed in a class, explain it.
They did lots of calculation, but at last they didn't get the exact result. I got very sad saying that they did hard work, but didn't fruitfully.
So any question about this, any student?
Just one
on this?
question.
Sure.
If we didn't show the y equation, will we lose mark?
Yeah.
Because the first question was you have to show the equation, that was 10 marks, that you have to develop the equation, and that is the 10 marks. And then the next question was to use this equation to find the missing values.
But Professor, it was stated like, I do have the result, the 0.3752, but it wasn't mentioned to show y. So I didn't click into y to show the equation. So will I lose mark for that? Because it was only mentioned to show the R square value, that's it.
We asked to
No,
show you the
you
R square values. I think the Shaikh has marked accordingly, according to the question. I
No,
think.
Prof, I deducted mark for that because in that question you clearly asked for the y equation.
Okay.
It didn't show, but
So I think we asked the regression equation.
Yep, Prof, you asked that. So I deducted some marks, not the whole. Prof, you can consider if you want to.
No. The way you have marked is fine. All right.
Excuse me.
Can I make one comment, sir?
Here.
So for calculating the y values for missing flow data,
Yes.
so if we exclude the flow 1 data corresponding to the missing value for flow 2,
Yeah.
the regression equation that we have developed, and either way, if we consider all the values, so those I mean, these two models give us the same results. So there is
Ali
no,
Ahmed,
yes.
I gave full marks for everybody.
Okay. So, I
But
mean,
the most accurate on A is you have to exclude those missing data points, and you have to only consider the years where you have the corresponding value for each year. When you are developing the regression equation, you should exclude those 3 years that I showed during the tutorial class, and then you develop the equation.
That's why I write this point.
Then you use the X value and then find the Y value.
Prof, they use the flow 2 value for the missing value. Who the student who used the flow 2 chart for their missing value, I gave them full marks because their way of calculating is correct. That's why I considered them.
Okay, that's fine.
That's all. And here the accuracy level can be increased by these three, considering these three topics: data length, appropriate transformation of data, such as log transformation, and accuracy can increase by using data from different stations nearby.
Okay, so I think that's all for the marks of the students. So really, I think for the final exam, now you have the project report mark. Project report mark probably generally easy a little bit. So I hope that you'll get good marks there. And then we have final exam as well. And in the final exam, probably because this is a final year student, final year subject, so I'm not expecting that many students will fail in the final exam overall.
Sir, do we have our question in final exam?
Sorry?
Any question from R in final exam?
Because the R is a kind of software, so you can use R. Like here in this exam, we have given R for GV distribution, so we can give something from R, which we have done in the class. And the next year, I will do quite a lot of R, because next lecture is software application, and I'll show the quite something about R, more things with R.
Okay, thank you.
Excuse me, sir. I have a question about the exam.
Okay.
So in question 1, we didn't use the t-test for because on equation sheet you provide to us, there's only degree freedom up to 30. So we don't have any access to the value of t equal to degree of freedom of 48.
So you can use the T, like if you consider that it's 30, up to 30, even if you can use the 30, that's fine. But if you search in the internet, there are a lot of T distribution tables that you will find, many of them.
Yeah, that's when I search in the internet, I find like they say if the degree of freedom is greater than 30, we can use the Z test straight away. So that's why I
that
use
is a very gross approximation in my opinion, because if you look for T distribution table, if you search in the T distribution table, you will see that the accurate ones, they have gone very high values of N, degree of freedom. That is a very gross thing. Like if you want to approximate that your T distribution by normal distribution at N equal 30, I think that may not be that accurate. But I think you have given some marks for that. I think for using Z distribution, Dr. Saika has given some mark, I guess.
I give some marks. Those who use Z value, I give some marks.
Is it 50%?
Yeah, Prof. You told me to give 50% for that.
Yeah, I think that's a very high percentage of mark loss.
Yeah, probably.
Excuse me, miss.
Yep.
Miss, so if like we didn't, for the second question, we like didn't get the graph from flow 2 to flow 1, we get 0 marks?
No, I gave 3 marks out of 10.
All right, thank you, Miss.
I think that's very generous marking. If I was marking, I would have given probably 0.
But lots of students did the same, so I just feel.
But that's fine. That's fine. It's always better to give some marks to the students if they have done something probably. Otherwise, a lot of
Their
students.
way of regression analysis is correct. They are using the correct equation, but they're considering data is wrong. That's why I considered some mark for them.
Okay. Okay, so let me release the mark to the students, and I think Gokan has taken the attendance. Is that right, Gokan?
Yes, sir. Yeah, I did it.
Okay, so any question or any suggestions by Gokan or Saika? Anything?
No, Prof. Thank you, Prof.
Gokan, do you have any suggestion or anything? Any comments?
No, all good, sir. Thank you. I don't have any.
Okay, so I think then we can finish the class here. So for your project report, we have given you 1 week extension. I'll give a notification in the views by today, and you can form your groups with 2, 3, or 4 students, and you can go up to 4,000 words in your project report, and I will allow you to submit. I will allow 1 week extension there. Any
Thanks,
question
Prof.
for anything? So no question? Okay, then we can finish it here. Thank you, everybody. So Gokan, do we have a meeting for anything?
Sure, if you don't have any question about the rainwater harvesting geometric analysis,
Yeah.
I have some question about the water in Bangladesh paper.
Okay, then we can discuss it there. We can discuss it. So I can maybe go out and then
Yes.
create another Zoom ID.
Yeah, you can end this one and we can join again.
Okay, so you can end this one and then join again. Okay.
Yeah.